Okay, so this week you will have a lab assignment to do. Okay, and there's two parts to it, so they're each worth a lab assignment here. Okay, and so it's under this week's module, and you'll click this, and it'll say go over to this. Basically open up these two PDF files. Okay. And one is called Lab 4A and one's called Lab 4B. These are from an online statistics textbook called Open Intro, which is a great textbook, and it's actually free. So there will be a few things that they do a little bit different from what we've covered in class, okay? Because the text, anytime you open an intro textbook, a lot of things are similar, but then just a few things are going to be different. Okay, so but anyway, I think it's still a good lab, and it uses R, and I think kind of gives you a little bit of a feel for sampling distributions and confidence intervals. Okay, so this first one, Lab 4A, covers sampling distributions. Okay. And so what we'll be looking at is some housing data from the city of Ames, Iowa. Okay, and so this city of Ames, they decided to release a bunch of information on houses and stuff. It's almost like it's kind of like Zillow data, but Zillow has all of their data kind of, they make it difficult to access easily, but Iowa, they publish this, and it's quite nice. So anyway, as you work through the lab, you're just going to kind of like read through this, and then whenever you see these instructions, you'll type these instructions into R. Now, depending on your computer, you may or may not be able to copy and paste these commands into R, okay? And sometimes if you copy and paste into R, it's going to give you an error, okay? And that's because, we're copying text from a PDF, and PDFs do slightly funny things to the text, and sometimes it'll insert a hidden character or a space or something, and so when you paste it into R, it might not work out, okay? And that's okay. If it doesn't work out, you can always fall back on the standard method of typing it in, okay? And I would recommend typing it in, especially because I think when you type things in, you kind of get a feel for what this command does, okay? So I'm just going to type it in, download.file, parentheses, quote, http://www.openintro.org/stat/data/ames.r, capital data, okay? Dest file, so it's kind of like the destination file is going to be ames.rdata. And what this command does is it goes to the internet and it downloads the file onto the computer, okay? Now what you don't want to do is you don't want to copy and paste this link and put it into your browser, because if you do that, the browser is going to try to open up the data file, and it's going to look like all of this garbled text and madness, and you can't really do anything with it. So you'll want to use this command within R to download the file, and it should work like 99% of the time. If your computer has some weird, I don't know, firewall or something preventing it from easily just downloading files from the internet, then you might run into a problem. But this, for most of you, it should be a non-issue. For most of you, when you type it in, it should say something like this: trying the URL, I downloaded the file, okay? And then you're going to type in load ames.rdata, okay? And so whatever your working directory is, it's going to basically create a file called ames.rdata, and then when you type in load, it's going to load that data file. And after you type in load, you should notice in the top right hand corner of your screen, it'll say, okay, it's got data called aims, and then it also created two functions. One is called contains and one is called plot.ci. Okay, and so this is the information contained in this R data file. Some of it is this data, and you can actually click this and it'll open up kind of this spreadsheet of stuff that you see. And this is just like we can take a look. Here is a house with 31,000 square feet of lot size, irregular lot shape, and I don't know, all sorts of stuff. It's whatever, okay, built in 1960. I don't know. Also, you can go through all of this stuff, okay? But we are going to focus on really just two of the variables. One is the size of the house, so that's the area, the greater living area, okay? And one is the sale price. So actually, what I'll do is do this side-by-side mode. So I'm just typing this in, area. This arrow says take whatever is on this side, gr.live.area, and store it into the variable area. And you can see that it has created something over here. Every time, it doesn't look like a whole lot is happening over here, but if we might notice changes over here, which indicates kind of like the creation of stuff here. Okay, we've got price, and over here we got aims $ sale price. Okay, and we see that has also been created here. Okay, and so so these are the things. These are kind of the sale price of the house, and then the square footage of the house that we're looking at. Okay, and it says let's create summary data and look at a histogram here. Okay, so we're going to just type in summary area, and it says, okay, the smallest house for sale is 334 square feet. The biggest house is over 5,000 square feet, so it's a very big house. Whereas the median or the average size house is around 1,500 square feet, which sounds reasonable to me. Okay, and we can also ask for a histogram of this, and it creates it over here. Perhaps we see something like this. Okay, and so most of the houses are between 1,000 and 2,000 square feet, but we have a right skew distribution indicating that some houses get really big. Okay, and then we do have a few houses that are quite small. But for the most part, we're between 1,000 and 2,000 square feet, or something like that. Okay, and it says exercise 1, describe this population distribution. So what you'll want to do is create some kind of Word document, or whatever it is, and you'll call this lab 4A exercise 1, and then where you're describing the distribution, you'll say the distribution of the house size, and you can call it gr.live.area, is unimodal and right skewed, etc., 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 right? So I'm not going to give you the full answer, but this is kind of a starting point for what you'll want to do. So so you can do this, and if you want, you can include supporting graphs and things like that. Okay, and so if you want to include like the histogram of this, you can click export and type in click copy to clipboard. Okay, and you can you can resize this to something else, and so you can click copy plot. So within RStudio, wherever the plots are being created, you do export and then copy to clipboard, and then you can come back over to Word and then just hit Control V, and ta-da, it'll paste the plot right there, and and just like any other Microsoft Word object, you can format it, okay, or whatever thing it is that you're working on, okay. And a lot of you guys figured this out for the first lab assignment, so I'm thinking this is going to be fine for you guys, okay. So so here we are creating a sampling distribution, and so if you guys recall what the sampling distribution is, we are repeatedly going to draw samples out of the population, okay, and in our case we have a population of 2,930 houses. This is our population, and so the sampling distribution is where we repeatedly draw samples out of this population. We're going to take the mean of each sample and keep track of all of those sample means. We're going to keep track of all of those y bars or x bars. And then after doing this many, many times, the resulting distribution of all those sample means, that is our sampling distribution, okay? And so, so this lab walks us through how we can use R to conduct such a thing, okay? And so it says we're going to try creating something called sample1, or samp1, and for this we use the function sample, and what we are sampling is we're going to sample the vector area. So where it says area, it's going to refer to this value over here where there's 2,930 square footage values there, okay? And we're going to ask for a sample of 50, okay? And so when we do that, we see that it has created a vector here of 50 values, okay? And so these are just 50 values drawn out of the population of 2,930, okay? So this this notation that we see in the corner, this basically says, there's these are integer values, and there's 2,930, and over here there's integer values, and there's 50 of them, okay, in sample 1, okay, and then we can ask, it says describe the distribution of this sample. So how would we do that? We would probably have to create a histogram of sample 1, okay, and so this is the histogram of the 50 values in my sample. We can also ask summary of samp1 and things like that, and we can see, okay, well, in my sample of 50 values, how does the median and the mean compare and stuff, and they're similar but not exactly the same, which is expected because this is a random sample of 50 out of the 2,930, okay, and so we can ask for what's the mean of samp1 and things like that. And so to build up the sampling distribution, this is going to be one of those values that we want to keep track of, okay? And again, with the sampling distribution, we want to repeat this thousands of times to get, thousands of these sample means, okay? And so, as you follow these directions, it will tell you, this is what we're going to do. And so here it says what we're going to do is we're going to build a loop that does this thing 5,000 times. So basically it's going to draw a sample of 50 values out of this 2,930, and it's going to record the sample mean of those 50 values, and then it's going to repeat that process 5,000 times, okay? And so you would type this in, and it says, so we're going to create this vector called sample means of size 50, of which we repeat the value 0 5,000 times, and then we're going to create this loop for I in 1 through 5,000. What we want to do is sample area comma 50 sample underscore means I, sample underscore means 50 I mean samp, and then we close this loop off, okay, and then and it's already done. It's created 5,000 values of these things, and we can ask for a histogram of sample underscore means 50, okay? So, oops, something. Did I type something in wrong? Let me just oh, I see. Yeah, I messed up there. Okay, so let me just say sample means 50. Okay, let me just type in all of this stuff again. So for I in 5,000, see, the computer is very sensitive. So I don't know if you guys see the mistake that I made. It's here I have mean of samp1 rather than mean of samp, okay? And that's going to be the error, okay? I think my eyes are kind of trained to notice kind of these letter by letter differences just because I've been doing this computer typing stuff for a while now. If you're relatively new to computer programming, I don't know, your eyes are probably not trained for this exact small precision detail stuff, and it's just it can be frustrating in the beginning because you're like, I feel like this is typed exactly the same, and then but if you go letter by letter, key by key, you might notice, oh, something is a little bit different, and it, if you do this all day, somehow your brain just starts to pay attention to these things, and it's not it's just a skill that develops over time, and it's just kind of funny, but it can be definitely frustrating in the beginning. Okay, so anyway, this is the histogram of this, and we get almost a normal distribution, maybe just a tiny bit of a right skew here, but overall this looks quite normal. Yes?
How do you return without executing what you've already typed? Like where you have the plus sign?
Oh, okay, so R will automatically, if the command you give it does not complete, R will automatically give you the plus sign saying, I need you to close off the command, okay? And so what happens is, what I did was typed in this thing for I in 1 through 5,000, okay? And then I created open curly brace, okay? Now, depending on your RStudio, a lot of times it will create the closing brace. Every time you do an open parentheses, it'll also create the closing parentheses, or the open quote, it'll also create the closing quote, just so you don't run into errors. I don't want to do this because if I do this, it's going to just run that, because it sees this as a complete command here, okay? So when I typed it, I deleted that closing brace, okay? And then so now R says, okay, I'm expecting this closing brace, and keep giving me stuff, or like, I'm waiting for this closing brace, right? So now you can say like, do this and do that and do this and do that, and then it'll keep asking for more stuff until you finally give it the closing brace, and then it says, ah, finally, and now I can run this stuff. And so again, early in your programming careers or whatever, this can be a source of frustration because you might accidentally close something off before you intend to, okay? And then when you close something off, it basically will execute the loop, and then you might try to give it commands that were supposed to be inside the loop, but the loop has already finished, so now you're just kind of giving it these separate things, and then R is just going to, maybe it'll try to do it, maybe it'll just kind of give you an error and say like, why are you giving me this, right? So that can be frustrating. Another thing that maybe a recommendation is in RStudio, create a new R script. Okay, you can do new file R script, or you can click this little plus thing in the corner and an R script here, and you can kind of type in the commands here, and so you can say, for I in 1 through 5,000, do all of this, and you can say samp is going to be sample area 50, and then sample means 50 bracket I is going to be samp and things like that. And then this way, and this will be up here, and then you can tell R to run this command. You highlight it and you click run, or you highlight it and you hit Control Enter, and it sends it down into the thing. And then here it says you have there are 50 warnings here, and so maybe I should see what these warnings are. And it says in sample means number of items to replace. So I've done something bad. In sample means sample underscore means 50. Number of items to replace is not a multiple of replacement length. Okay, I think it's because I'm like trying to overwrite stuff here, so I should probably clear out my sample means 50. Okay, let's see if this works. Oh no, it's still complaining to me. Okay, well, this is the life of I'm just I can't figure out what I've sample means oh this is, see, I forgot to put mean around samp here. Okay, and that's why it's giving me errors. Okay, and so now when I do this, it runs without complaining. Okay, so so yeah, you know, you when you type stuff out, you know, it's very easy to make a small mistake. Okay, I make small mistakes all the time, and things don't run the way I expect them, and you get these warnings and stuff like that, or errors if it just won't run. R will basically try to do whatever you ask it to do, and but it will say like, I'm not sure if this is what I think you wanted me to do, and it'll give you a warning. Okay, and then if it just can't do it, it'll give you an error. Okay, so R will, whenever you give it a command, R is going to try to do it, but if it suspects something is funny, it'll give you a warning and things like that. So it's usually good to figure it out, and then it's always slightly cryptic, right? It says like number of items to replace is not a multiple, and so a lot of times you're just like, well, I don't know what you're talking about, but then you go back to the kind of the model code that you're supposed to do, and you go letter by letter, and you go, oh, this is the mistake I'm making. Okay, the lab in here explains, you know, how this loop is working and all of this stuff. Okay, but basically the point of this first lab is to try out these sample means, and then try out sample means of different sizes. Okay, so this was when we were taking samples of size 50 out of the population of basically 3,000 houses. You know, what happens if I take samples of size 10? How does our sampling distribution change then? Okay, and so here, you know, I would change sample means. I would create a new place to store my sample means, and I'm going to call that sample means 10. I'm going to basically run the same code, except this time the command for sample is draw only 10 values rather than 50, and then take the mean of that sample of 10 values and store those means into the object sample means 10. Okay, and then so we just run these commands, and it does that, and then we can create histogram of sample means 10. Okay, oops. Okay, and this is the histogram of sample means 10 versus the histogram of sample means 50. Okay, let's do breaks equals 25 for both of these. Oops. Breaks. Okay, so this is histogram for sample means 50 versus sample means 10, and we see with sample means 10 we still have a little bit of right skew, and when we see the kind of the spread is quite high from basically around 1200 to 1800 or something. Sample means 50, our spread is a lot smaller, maybe 13 something, 1360 to 16 whatever, the bulk of our data values are there. It looks a lot more symmetric and things like that. Okay, and so you'll get to explore a little bit of this in the first lab here. Okay. Does this seem okay? Okay. All right. And again, just if you try to copy and paste and you get all these errors, it's probably better to just type straight up. Okay. But then make sure you type exactly what you see. Okay. And then lab 2, or the second part of this lab, uses the same data file, and now we're going to create confidence intervals, okay? And so in this case, we can, because we actually have the data of the population, all 2,930 values, we can take the mean of all of these values, okay? And we see that the mean of all these values is 1,499.69, basically 1,500, okay? And what we're going to do in this lab is we're going to draw samples, okay, from the area or the population. For whatever reason, they've decided to rename area to population, which is fine. Okay. So we call that the population, and we're going to draw samples. We're going to start off with drawing samples of size 60. Okay. So this is our first sample will be sample, the population. We're going to draw 60 values, okay? And then we're going to calculate the sample mean, which is the mean of our sample, okay? The sample mean, it says, of our 60 values is 1,441, okay, in this case, okay? And then so here we're going to create a confidence interval, okay? And this is where the instructions for the lab differ from what we learned in our class. So in our class we learned it should be the sample mean plus or minus t star times the standard error, okay? And here it's basically the same thing. We calculate the standard error, which is the standard deviation of the sample divided by the square root of n. So that's fine. But they're using 1.96, okay, and that's coming from the normal distribution or having infinity degrees of freedom. So in our class, we've learned this number should be compensated a little bit to maybe like 2.1 or something like that, something a little bit larger. But for the purposes of this lab, you can leave it 1.96 if you want to. Figure out what value you're supposed to use for t star. That's fine. It doesn't really matter. I mean, it makes just a minimal difference in terms of what happens in our lab here. Okay, but basically we create a standard error. So we're going to say the standard error is the standard deviation of our sample, and then divided by the square root of 60. Okay, so we get a value for our standard error, and then we're going to create a value for the lower bound, which is going to be our sample mean minus 1.96 times the standard error, okay? Maybe, and then the upper bound is the sample mean plus 1.96 times the standard error, okay? And then so this the command C just basically sticks them together into a certain into one line, and so we get our confidence interval goes from 1303 to 1579 or something like that. Okay, and so if we think about if this is our confidence interval and we know that the population mean is 1500, we have managed to capture the population mean within our confidence interval. Okay. Basically, what we can do is we can create a loop where we are going to repeatedly draw different samples, and based on each sample, create a new confidence interval. Okay, so each sample will be a new value of new set of 60 values, and then with each of those samples we're going to calculate the sample mean, calculate the standard error, and go plus or minus the margin of error. Okay, so we're going to just build a loop. So we go for I, and 1 through 5,000. Oh no, just 1 through 50. Okay, we're just going to do 50 loops. I forgot. This is different because we're going to graph all of these things. Okay, so I want to create a vector called sample mean, which creates 50 missing values, 50 NAs, and then sample standard deviation, which is also going to create 50 missing values. Okay, and then with every iteration of the loop, what I want to do is draw a sample from the population. Of size n. So here we're going to draw samples of size 50. Oops. What do I want? And then we're going to calculate the sample mean and the sample standard deviation. Okay. In position I, we're going to calculate the mean of our sample and then the sample standard deviation. Oops. Okay, so we have that, and we're going to run that. Okay, and that's done. And then we have, I'll try copying and pasting this. We'll see if this works. That looks like it worked. Whoops. So, your mileage may vary on this part. Okay, we got a vector of lower and upper. And then we're going to use the built-in function, or not the built-in function, but this function that was created for us called plot_ci. Okay, and so let's try this. Okay, and so running plot_ci, it's going to create a bunch of confidence intervals here. Okay, and so what this plot is so I ran the loop 50 times, okay? And so the first time I ran it, my sample mean of 60 of those 60 houses I drew ended up here, and when I created the confidence interval, it went from, I don't know, down here up to here, okay? And it managed to capture the true value of basically 1,500 within its bounds, okay? And so all of these confidence intervals managed to capture it, but I happen to get 3 confidence intervals that just missed the or missed the population mean. Okay, and so this one just barely missed it, but it probably went from like 1,300 to maybe 1,499 or 1,499.1, where the true value is 1,499.7. Okay, and so. We would say, I'm 95% confident that the population mean is between, 1,300 and 1,499, which would turn out to be wrong, okay? But again, when you create a confidence interval, you have a random sample of data and you create a confidence interval, you don't know if it's one of these, quote, correct ones, or if it's one of the ones that missed. You have no idea, okay? But basically, you are counting on the fact that when you create these confidence intervals, 95% of the time, you get it right, okay? You don't know if yours is the right one or the wrong one, but you're counting on the fact that overall, 95% of the time it's right, and so you say something like, I'm 95% confident that I'm right, even though I have no idea, okay? And again, whenever you create one, you have no idea if the true value is close to the lower end of the confidence interval or the higher end of the confidence interval. This is just kind of one of those things of life where you don't really know, okay, until you've gathered more data, and that's it, okay. It's so this is the second lab, okay, and so that's that. Are there any questions on this? And I apologize, I haven't gotten around to grading your first labs either. I know that's like huh?
Just kidding.
Yeah, so I know it's I'm quick to grade the other things, but the labs, for some reason, I'm always dragging my feet to do it. So
You're so fast with the tests because
yeah.
you have to like make up for the.
I know I'm slow for the labs there. So okay. Anyway, good luck. We'll see